Okay, I know I start 3 seconds early, but I think we'll survive.
No.
Wow, it's pretty much unanimous. So we're done with electricity and magnetism. Completely done with that. The only time that will come back fundamentally is when we have our final exam. So moving on with optics. Yeah, there she is. Moving on with optics, we're going to talk about geometric optics today and image formation. So to get started, oh yes, I am using something else so I can draw stuff better. We're not going to do any woo claps, so don't worry about that. Plane mirror formation. Plane mirrors form an image. How do I know this? Because when I look in a plane mirror, I see myself. What I see is called an image. The thing that caused that image is called the object. So when I look in the mirror, I don't see myself. I see light rays that came from me, bounced off the mirror, and then got to my eyes. So I know you might say, but the light rays came from you. Yes, but they had the intermediary of bouncing off the optical device, in this case, the mirror. And the easiest way to explain where the image is with a plane mirror. Now, when we say plane mirror, we don't mean regular everyday. We mean flat. So a plane mirror is a flat mirror. The easiest way to explain where the image is to recognize that our eyeballs have an opening that is not just a point. That is, there's light coming in from the top of the pupil to the bottom of the pupil. And so this picture is showing rays going to the bottom of the pupil and the top of the pupil. And the eye takes the direction of those rays and extrapolates to where they were at one location, says that's how far away it is. So if you have the top of this bottle, light rays go from this bottle top, and they go in all directions. So there's light rays that are going like this and like this and like this from the top. But the only ones that make it into the eye are ones between those two lines that shows coming from the top. And so they come here, they follow the angle of incidence equals the angle of reflection, reflect back. The eye sees them, and then the eye extrapolates back and says, those came together at this point. Now, based on the symmetry here, that the rays here are spreading, and then the amount they're going to converge is the same amount, because they're the same stinging ray, then that means that the distance behind the mirror is going to be the same as the distance in front of the mirror. So the image is formed behind the mirror at a distance equal to the distance the object was in front. So if I stand in front of a mirror, here's my mirror. I know. If I'm 1 meter away from the mirror, then the image of me that I see is 1 meter on the other side of the mirror. Simple enough rule. Now we have some interesting things. The first thing I want to point out that's interesting is one of those fake things that you read about on the internet all the time. So, you know what a two-way mirror is? Mm-hmm. Tell me what a two-way mirror does.
You're supposed to be able to look into it, or you're supposed to be able to look through on one side and then on the other side.
Wait, but doesn't that work on both sides as long as like the light's off on one side?
Oh, somebody that's a little ahead of the game. That's right.
I watch crime shows as well.
Have you read those little things on how to know, like when you go to a hotel room or a bathroom, if it's a one-way mirror or not?
Put your finger on it.
Yeah, that's stupid. That is not the way things work. Because as Andy said, they work both directions. A one-way mirror is fundamentally, I just use 50% for an example, it doesn't have to be 50%. But it's coated with a reflective coating that's going to reflect half of the light that hits it. Half the light goes through. And so then if you have one side is bright, there's a whole lot of light there, which means there's going to be a whole lot of light reflected. And so somebody in the room that's bright is going to see their reflection. If the other side is dark, there's not much light there. So there's not much light reflected, but there's a whole lot of light from the other side that came through. And so they see what was on the other side. If you have bright lights on both sides, what do you see?
You see through.
You see both. You see your reflection as a faint ghostly reflection. You see what's on the other side as a faint ghostly thing. What was your question?
So then would the reflection that you see be dimmer than in a true mirror?
That's right.
Would you actually
Yes.
be able to test by carrying around a pocket mirror and holding it up?
I suppose that would actually work, yeah. If you could differentiate, it's kind of hard to differentiate, but.
Right. Cool.
So the whole thing about touching the mirror, well, where's the reflective coating on most mirrors?
On the back.
On the back side. So you usually have a gap. You have glass up here. You can touch the glass, and then there's a reflective coating behind it. It's behind it because they want to protect it, right? They don't want the reflective coating to be on the front where the elements get to it, people can touch it. And of course, if it's a two-way mirror, where do you suppose they put the reflective coating?
In the middle.
Yeah, they sandwich it in the middle. In both cases, if you touch the mirror, you're going to have that gap because there's glass between your finger and the reflective surface. So that is not a way to differentiate if it's a two-way mirror or not. So what's the key of the two-way mirror? Fundamentally, you have a 50% roughly reflecting mirror, and then bright on one side, dark on the other. And most people know the bright and the dark side. That's why you have the jokes like somebody who's trying to identify who the bad guy is, and the janitor comes in, turns on the light, and then the bad guy can see who's identifying them. Maybe you haven't seen those. Okay, just wanted to point that out. Next thing is sign conventions. Sign conventions, how do we call what do we use for the name of the image position, the name of the object position, and our sign conventions? Here's a table that breaks it down. The object distance, this says P. I tend to use D with the subscript of O for distance object. The object distance is positive for any real object. Real means it exists, okay? So for any real object, the object distance is positive. And something just happened on my tablet. We'll just pretend that didn't happen. Hopefully it didn't stop the recording. Virtual image. What do you suppose virtual means? Not real. Virtual means that it's not real. It means that we have an extrapolation of rays to make the object, but the rays don't really originate from that point. So a virtual image, and we'll see examples of that later, but a virtual image has a negative, or a virtual object has a negative object distance. Then image distance, which I usually use a D with the subscript of I for image. If you have a real image, if the rays really cross, the image is formed when the rays meet. So if the rays really meet, you have a real image. If the rays really meet, you can project it. So the image you see on the screen here is real. You know that because you can project it onto the screen and see it on the screen. A virtual image is where they're extrapolated. So if we go back to once again, I keep trying to use this. I am so ingrained. If we go back to this picture, the light rays didn't really meet here. So this is a virtual image because the light rays didn't really meet. This is a real object because the light rays really were together there at the object. Go ahead, Andy.
In what way you said this is a real image because you're able to project it, but in what way are the light rays meeting?
Okay, so what's happening, and this is stuff that's coming up, but what's happening is we have a lens in the front of that thing. And so we have light, to make life simple, you have in the projector.
If it's coming up, I don't mind waiting.
Well, it's good to cover it now. You're curious. You have the object, which for our purposes, we'll treat it like it's just a little TV screen. So you basically have a little TV screen, and then you have a lens out here. And so light from the top of that TV screen, and I'll use red for light from the top of the TV screen, is going out in all directions, and I only care about the light that hits the lens. And then that lens makes the light come back together. And when it comes back together, if we put the screen there where it came back together, then we're going to see it in focus. In focus because all of the rays that left the top of my object come together at the same location. And so we have, hitting right here are all the rays that came from a piece of that little object, TV screen being our object.
That makes sense. Thank you.
Yeah. Okay, so real object means positive object distance. Virtual image, this one here is going to confuse you. If it's a mirror, then if it's on the opposite side, it's a negative image distance. If it's a lens, if it's on the opposite side, it's a positive image distance. But the real key that makes it so you can figure it out is the light always stays on the object side of a mirror. Like the light doesn't go through the mirror. And so if the image is formed on the side that the light is, it's going to be a positive image distance. If the image is formed on the side where the light is not, that is, if it's a virtual image, that's a negative image distance.
So then with the projector, are they both positive?
For the projector, it's both positive because the object is on the side the light is on for the object. The image is on the side the light is for the image. So they're both positive. Yeah, that's why I said it's confusing. So in my mind, I always think about where's the light. If the image is on the side where the light is, then it's positive image distance. If it's on the opposite side from where the light is, it's a negative image distance.
Wait, okay, so the reason that the real object is real is because the mirror, it can see back on itself. Why?
The reason it's real is because the rays actually meet there. Right, at the source for any actual object, the rays, of course, are coming from that object. And so they were all together here. And so that's what makes it real, if the rays were all together. If I have a plane mirror here, then when you look at it in your eye, you would see it over here. But the rays aren't actually there, so it's virtual. You're extrapolating. So if it's an extrapolation, it's virtual.
So it's trying to say, like, for that virtual image that you can't actually see that even though, or it's not really even though you can see it?
You can see it, that's correct, but it's an extrapolation. There's nothing at that location. If you put a piece of paper there, you'll see nothing on it.
Because you're seeing it somewhere else.
Because
the real object is somewhere else.
Well, it's not where the real object is. It's that there are no light rays where the image is. It's an extrapolation because our brain is just extrapolating to there's where it was. And so, you've seen things like people or animals that are introduced to a mirror for the first time. They don't understand. They don't understand that something is on the same side of the mirror as they are. They think it's on the other side because their brain is just extrapolating. It doesn't understand there's something in the middle that's changing the way to interpret it. We grew up with mirrors.
It's not the same thing as like in the desert when like you're walking or whatever and you can see like water in the distance.
A mirage. Mirages were at the end of the lecture that I didn't get to cover last class period. But mirages are a result of refraction. You have two fundamental types of mirage. One where you look down at the ground and you see what looks like water. And that's because the ground is very hot. On a hot day, it's only occurs on a hot day. So the ground is really hot because it's absorbing light. And so the air right above the ground is really hot. And that air that's really hot has a lower index of refraction. And so light rays from the sky come down, and with the changing index of refraction, remember, what is the index of refraction telling you? It's telling you about the speed that light travels through. The lower the index of refraction, the closer to 1, the faster the light's going. So the light goes faster as you get closer, and because it's going faster, it's going to bend away from the normal, and so the light coming down from the sky is going like this and curves back up. And so when you see the mirage, when you're driving down the road and it looks like there's water on the road ahead, and then you get there and it's not there, that's a mirage. And what you're seeing is the sky coming down and refracting back up to you. So that's the typical mirage. The first time I saw that, we're driving out through the Mojave Desert, and I was like, oh, sweet, we're going to hit this puddle of water. It's going to be great. And it never came. And I was so confused because I was a kid and I didn't know what mirages were. The other kind of mirage occurs when you have a temperature inversion typically above water. And so once again, different temperatures give you different indices of refraction. And if it's hotter up higher and cooler down lower, then light from below comes up and refracts back down. And so then you see like buildings or ships in the sky in that kind of mirage. It was something I meant to cover. I tried to cover, but didn't get there on Monday. Okay, so I'm going to stop doing that. Sign conventions. We have this thing called focal length. We haven't covered that yet, so you don't know that yet. And we have magnification. Magnification is defined as the height of the image divided by the height of the object. So if we look in this picture, here's the height of the object. Here's the height of the image. And just take a rough guess, how do those compare?
They're the same.
They're the same. And they're both upright. In that case, if it's upright, it's a positive height. So it's a positive image height, a positive object height. The magnification then is going to be 1 because they're the same height. If I'd had an image that was like this, then that's inverted, and I would have had a negative image height and a negative magnification. So negative magnification just means it's inverted, it's upside down. So that's the magnification numbers. Now let's, what? Okay. Let's get to doing stuff. Now I have here a website you can go to and do all kinds of complicated stuff with light and see how it works. I will probably go to there, but I want to start now with some demonstrations of what's really going on. Because with optics, unlike with electrical stuff, we can see what's going on. It's much more accessible, which I think then makes it much easier to learn. So here I have a little laser ray box. It's sending out laser rays, laser beams, traveling as a straight line, and then I can put things in front of it. So we've learned about refraction. We've learned about light bending when it goes from one speed into another. So here's just a piece of polymethyl methacrylate, lucite, or whatever you want to call it. So I put it in here, and you can see that the light rays bent when they went in, right? And then when they came out, they're going the same direction. This is just like what I had you do in class for the calculation. And if I bend it more, what am I changing as I bend it more? The angle of incidence. And because I'm changing the angle of incidence, Snell's law says that the angle of refraction is also changing. So you can see that how much it's bent varies with the angle. And now we see some weird things going on. There's still light coming out here, right? Keep going, and it will eventually get there. Okay, well, actually, no, it's still there. Light goes in. You can see it going up like this, and it looks like it's coming out, but I still need to go more, apparently. It's a hard life. Just go with this. Makes life easier.
Hold up.
Here the light is coming in. What's it doing at the first section?
What shape is that?
First surface. This is a hemisphere. Or not hemisphere because it's flat. It's a circle.
Sweet.
What's it doing at the first surface?
It's refracted.
Refracting. Which direction is it refracting?
And
In. Why in?
because they're all going into each other.
Well, because it refracts, it's going into a slower speed material, so it's refracting toward normal. Now, when it comes out here, you can't really see it changing direction, but it is a little bit there. If I take it and rotate it, I can do some weird things like Now what's going on?
I agree with craziness.
Crazy things are happening. What's it doing at the front surface? It's bending, it's refracting. What's it doing at the back surface? It's reflecting. Why? Here are 3 of them are refracting at the back surface, and 2 of them are not.
That's silly.
It's silly. Okay,
Isn't it because it's the shape and like the angle of refraction and whatnot?
Snell's law is that, I'll just turn on some more lights. Snell's law says n1 sine theta 1 equals n2 sine theta 2. On this back surface, I have n1 is equal to 1.49. Well, let's put 3 of them in here. Here I have n1. In here I have n2. And then out here I have n3. So going from the second to the third medium, so I better put 2s and 3s. N3 is a smaller number than N2. If I want to solve for theta 3, I have sine of theta 3 equals N2 over N3 sine theta 2. Putting in my numbers, that's 1.49 over 1.00 sine theta 2. Well, here's the thing. This fraction out here is bigger than 1, right?
Yeah.
Well, what's the biggest that sine theta 3 can get?
1.
It has to be less than or equal to 1. So I put less than 1 because we're going to, here, less than or equal to 1. Sine theta 2 is kind of how I have the light coming in, so that's something I can adjust. Well, that means there's certain angles for theta 2 that are going to make this value, this whole right side, bigger than 1. If this whole right side is bigger than 1, it doesn't work. You can't have refraction in that case. So you can have no refraction in that case. Well, the light can't disappear. It has to go somewhere, so it reflects. So we call this here total internal reflection. And so what's my condition for a total internal reflection? If this comes out to be bigger than or equal to 1, we have total internal reflection. So we call the angle critical when it's equal to 1. So I put theta critical for the angle where it's going to start reflecting instead of refracting. And so then I can solve this. So the critical angle is the inverse sine of the medium it's going into divided by the index refraction of the medium it's going into, divided by the index refraction of the medium it's leaving. So in this case, that would have been inverse sine of 1 over 1.49. Now, of course, if you're going from diamond into air, that would be 1 over 2.42. It'd be a much smaller angle than if you were going from plexiglass into air. Actually, I think it's plexiglass. It could be acrylic. Lucite, plexiglass, polymethyl methacrylate are the same.
And n is a number that is like a constant. That's
And n is the index refraction. I actually, my next slide, okay, it's not my next slide. I do have a slide here that reminds us what n is, but n is the index refraction, which is N is the speed of light divided by the speed in whatever that medium is. So in this, the speed in the medium is equal to the speed of light divided by N, which is between friends. Which is roughly 2 times 10 to the 8 meters per second. Okay, so we saw the total internal reflection there. We'll turn the lights back off and continue on with the demos. Just takes a while. Now I'm going to change and go to mirrors. Why mirrors? Well, because mirrors is what we generally cover first because they're simpler. I don't know where I put my eraser, so I shall not worry about erasing. So for mirrors, I have 2 kinds of mirrors. This here is concave. You see the curvature? So if I put the concave mirror here, the light reflects following the rules we already learned. Angle of incidence equals angle of reflection. But what do you notice about those rays?
They get bent back into each other.
They get bent back to each other. We call that converging. So this is a converging mirror. Converging because they come together. Now, if you measure the radius of curvature of this surface, that is, if it was a complete circle, what would the radius of that circle be? We find that this distance here, which we call the focal length,
Be the radius of the circle.
it's 1/2 the radius of the circle. Geometrically, you can show that pretty easily because the light is bending twice as much as it would need to bend to go to the center because the normals would all meet at the center. And so since it's bending twice as much, it meets about halfway. Now I said about halfway. If I'm honest, the circular shape doesn't really focus the light at one location. The reason it doesn't focus the light at one location is because when the light is hitting the top, it's bending a little too much. Hitting the bottom, bending a little too much. So if I take this off, you can actually, well, you're probably too far away to see, but it's actually coming together in places ranging between there and there. It's not perfectly focused. To make it perfectly focused, I would need a parabolic shape. So if you have a dish for looking at a satellite, they're parabolic shaped. They're a parabolic dish. Why? Because if you're focusing on something that's very far away, you need to have a parabolic shape rather than a spherical shape. If you want something that's of intermediate distance, then you actually need an ellipsoidal shape. We're not going to worry about the parabolic shapes and ellipsoidal shapes, just something that's real out there to think about. So we have a focal length, and the parallel rays meet at the focal length. That's how we define the focal length. Focal length is the distance from the, in this case, mirror, to where the rays meet if you had incident incoming parallel rays. And as we worked out, as David said, well, we didn't work out, we talked about it. The focal length is 1/2 the radius. Now I'm going to change to this mirror. This one is convex. The mirror surface is pushing out. If I put that here, what's going to happen?
It's going to reflect everything out.
Okay, it's going to reflect everything out. Let's do it. My eyes got adjusted so I could see where that was. And sure enough, it reflects everything out. Do the rays meet? No, they don't. But they virtually do. That is, if you're looking at this with your eyeball just extrapolates back and says, sure, this one here was going like that, this one here was going like that, this one here was going like that, this one here. And so they all met right there. But those are extrapolations. That's a virtual focal point, right? Virtual because the rays aren't really there. But it still has this same rule that virtual focal point is the radius divided by 2. It has a negative focal length if it's a virtual focal point. So a convex mirror has a negative focal length. And we call it diverging because the light spread out or diverged. Whereas the concave has a positive focal length, and we call it converging because the light comes together. So that's the difference between concave and convex mirrors. I'm going to go back to normal and talk about a few more things before we look at some more cool stuff. Yeah, I will go ahead and go to this. Don't think I can just click on it. But, well, no, apparently I can. So here is the simulator. And it allows you to do all kinds of optic things. So I'm going to put a beam on there. Maybe. It worked. It worked differently on my desktop, probably because of different touch controls. Didn't mean to put a second one. Reset. Beam. Yeah, got to use my finger. Maybe it'll work. Maybe it won't. It doesn't work nearly as well the way my tablet is as it does on a PC. But there's a beam. And then you can put on a mirror, and you can put on a segment, which is a straight line. See if I can put it on there. Yeah, I can't control this the way I could on the computer. It's probably set in tablet mode or something like that is the problem. Or you can choose a circular arc. So you can put a circular mirror on there, maybe. So you can simulate these things. It's clearly not working on my tablet with the touch screen. Oh, wait. If I turn that off, will it work? Yeah. I think it'll work with that turned off. Beam. No, still not working. Okay, so I won't spend any more time on this because it's just not responsive right with the touch screen. But you can simulate the things we're doing to see how rays work. One of the things that is cool that you can do, I'm going to try this just because, Yeah. Well, there I have somewhat a circular mirror. We're just going to go with that. You can look at the rays. That's what light is actually doing. Or you can turn on extended rays and see what the extrapolations are doing. So you can see the extrapolations along with the actual rays. I'll just have to go back. I didn't realize the touchscreen was going to be a problem. Okay, so for spherical mirrors, real images of real objects are always inverted. If you form an image, it's going to be inverted. I would have shown you that on the previous thing, but yeah, it didn't work out. Virtual images are always upright. Now, with that said, let's take this mirror. What kind of mirror is this? Convex or concave? It's concave. Concave because it's inward. Is it a converging type or a diverging type?
Converging.
It's which one? Con or di? It's converging because parallel rays are going to come together. If it's converging, you can make a real image. So I'm going to have Anna be my guinea pig. Do you see yourself in the mirror?
Yes.
Okay, describe what you see.
I'm upside down.
Upside down, so it's an inverted image. What else? Bigger or smaller?
I don't know. Smaller?
Okay, I'm going to move farther away. Is it bigger? Do you still see yourself?
Yeah.
Bigger or smaller?
Smaller? I don't know.
Well, just pay attention to what happens to size as I come closer to you. As I come closer,
Bigger.
Okay, it's getting bigger as it comes closer.
Yeah.
Now, what do you see now?
I'm very large.
Very large. So now it's bigger than reality. It was smaller than reality back there. Magnification is changing.
Yikes.
What
Okay.
do you see now, Anna?
Nothing.
Nothing.
How do you not see it?
Because it's too big.
Because the image is forming behind her head.
Wait, what?
They see it? Hold up.
Yeah, they can see it.
Oh, I can't see.
Wait, so then light is bouncing off Anna like here and then converging
That's
back,
right.
like, back
That's
here.
right. That's exactly right.
Yeah, but it's not, you don't not see, oh, you do not see.
Yeah, you do not see.
see.
Because the image is behind your head. You can't focus on things behind you.
Well, it's-
It's upside down stool that it's
Oh, shoot.
It gets really good.
But now if I get even closer, now what do you see? Now it's right side up, bigger or smaller? It's right side up and bigger. If it's right side up, is it real or virtual?
So then with
It's right
It's right side up, it's virtual. What's the question?
Concave ones make it the ones that like are for a like makeup mirror, whatever the girls use.
Well, let's look at what we get with the other shape. So, going back with Anna, because she's been a good sport. So if you look at yourself here, are you upright or inverted? Is it real or virtual? Virtual because it's upright. Is it magnified or smaller? Smaller, okay, so it's diminished. What's happening as I get closer?
It's becoming bigger.
Bigger.
A lot.
Has it turned upside down?
No.
Did it ever get to where you couldn't see yourself?
Oh, okay.
So that's because it's a virtual image. It's forming on this side. It was always in front of you the whole time. It never went to behind you.
Oh, whoa.
So this is why, like, when you're in those parking garages, so they put those mirrors and they're curved.
They put them like this so you can see a wide angle. But the image you're seeing is behind here, and so the distances aren't, what you're thinking.
But like, if you just put that in there, it would be useless. Like, you
Right, if you put that in, it wouldn't be very useful. Everything would be inverted, for instance. That wouldn't be the goal. And when you look at your passenger side mirror and it says objects in the mirror are closer than they appear, it's because they're using this kind of mirror so you can see more cars. But as a result, they look like they're farther away.
But they still like have blind spots.
Yes, but you have less of a blind spot. Okay, so we could see there's a difference between the real and the virtual image. And it had to do with the concave. The concave could make both. The convex could only make virtual. And with the concave, it depended on the distance between the object and the mirror if it was going to be real or virtual. So we are not going to we are not going to show the rays right now. Instead, we're going to go straight to I told you we're not going to use, so I'm going to skip over that. The mirror equation. This is an equation that we get from geometry that we can use to find where the image is if we know where the object is, where the mirror is, and what the radius of the mirror is. So first we have the equation that David reminded us of. The focal length is rays divided by 2. And then we have this equation here. 1 over the focal length equals 1 over distance object plus 1 over distance image. Now let's do the easiest thing first. If I have a plane mirror, a flat mirror, we already saw the picture here. And where did we say the image was formed? From looking at the picture and talking about the rays diverging, where did we say it was formed?
On which mirror?
The plane mirror, the flat mirror.
Behind the mirror.
What distance?
Equidistant.
Equidistant. Okay, so we remember that. Now we're going to check this against those two equations. So for that case, for a plane mirror, what is the radius of a flat surface? It's the opposite of 0.
Infinity.
It's infinite. Because if you take all of the normals to the surface, the radius is the place where those normals meet. Where do parallel lines meet? Okay, never or infinity. And so the radius is infinity for a plane mirror, which means the focal length is infinity over 2, yeah. Which is still infinity. Yeah. No, I mean, you're right. I should have written it that way. And so if I put this in, 1 over the focal length is equal to 1 over infinity over 2, or if you prefer, 2 over infinity, which is, what's 2 over infinity?
0.
Equals 1 over distance object plus 1 over distance image. Well, the second part was this right here. I just repeated that. 1 over focal length equals 1 over distance object plus 1 over distance image. But for the plane mirror, 1 over focal length is 0. So that means 1 over distance object plus 1 over distance image is equal to 0. What's the only way that can be true? Well, no, mathematically.
Do you mean that like because infinity is in the bottom of zero, which is a rule?
That's a rule, yeah. No, I'm asking, what does this say about distance object and distance image? They have to be equal in magnitude, but opposite in sign. Right? So 1 over distance object plus 1 over distance image is 0. So this demands the distance image equals minus distance object. So just plugging that in, because there seems to be some confusion. What we had here was 0 equals 1 over distance image plus 1 over distance object. If I was solving that for distance image, I would first move them across. I'd have 1 over distance image equals minus 1 over distance object. And then, if you want, cross multiply. So distance object equals minus distance image when you cross multiply. So for the plane mirror, these equations say the distance image is minus distance object, which, conveniently enough, is what we had determined from saying the extrapolation of the rays is where the image is. Now that's a plane mirror. Here's something that's not a plane. An object that is 2 centimeters tall is placed 10 centimeters in front of a concave mirror with a radius of 15 centimeters. Is the mirror... Obviously, I put these questions in before I added that. It's concave. I was going to go with if the radius is positive, it's concave, and I figured I'd better be explicit and forgot to take out that question. So it's concave. What's the focal length? Okay, it's radius over 2. So that's 15 centimeters over 2, or 7.5 centimeters. I want to make sure people know where it came from and not just say, well, David got it, but I don't know how. Is the mirror converging or diverging? How do you know? Because concave is converging. Now, I emphasize the cons, but convex also has a con, so.
And the other one is
Convex would have been diverging. What is the object distance? Okay, because the object was placed 10 centimeters in front, distance object equals 10 centimeters. What is the image distance? I'm going to have to calculate it. I'm going to start by drawing, and you're going to have to learn to do geometric optics. On the next test, you're going to have to do a drawing for one of the questions. And it's going to be graded on the accuracy of the drawing, not on getting the right answer. So in doing this, first you draw what we call the principal axis. The principal axis is the axis that goes down the center of your element. In this case, it's a mirror. So then I put my mirror here. I drew it like a mirror, right? Like a concave mirror. You know what we really do usually? We're like, that is too hard. I am going to draw a vertical line for my mirror. And then I'm just going to go like this to indicate, oh, it's concave. The reason is our mirrors need to be flat for the most part. That is, if we have too much curvature, then we have the focus comes out the wrong place. Remember I said spherical is not really the right shape. We draw them as flat because our calculations are based on what we call paraxial rays. Rays that are close to the principal axis and close to parallel to it. And so if you're close enough to the principal axis, you really magnify, any surface is going to look flat. Next, I'm going to mark where the focal points are. So here is the focal point. There's only one focal point for a mirror. So there's the focal point. Actually, usually we use like a capital F for the focal point, and the distance is lowercase f. It doesn't really matter though. And then I need to put where the object is. Now that focal distance was 7.5 centimeters. And my object, and the object is drawn as just a vertical line. That's not it. Okay, so a vertical line with an arrow on top. That's the traditional way we do it. What was that? Go ahead. Well, it's not double, but it's bigger than 7.5. So there I have it drawn out. Now we will learn next class period about the rays to construct the image. But for now, I want to make sure we know how to draw this, and then I'll finish the drawing when I do the rest of the calculations. You have questions you need me to answer, Anna? Or is it all good? Okay. Not asking to be troublemaking, but to make sure there's not a question I didn't ignore. So now I look at that mirror equation, and I know what F is, and I know what DO is. I'm looking for DI. So if I solve that for DI, somebody has already done the math for us.
And because this is all in centimeters already, we don't have to convert, right?
Is DO negative?
DO is positive. So I have 1 over 7.5 minus 1 over 10. I mean, we could try to get a common denominator, and we would have 10 minus 7.5 over 75. Invert that, 75 over 2.5. Yeah, it's, I was just doing the math in my head. You have, well, no, it should be over 2.5. Is that third? Let's just do the math. 1 divided by 7.5. Oh, I added instead of, I don't know what I did. 1 divided by 7.5 minus 1 divided by 10. And then we take the inverse of that, which I'm sure is on this calculator somewhere, but I don't see it. I have x to the minus 2.
That is strange.
Yeah, that is strange. You'd think you'd have, oh, there it is. Second function, that. And yes, it gives me 30. And actually 7.5 over 2.5 is 30. So the distance for the image is 30 centimeters. So that means that my image would be out on the right-hand side, and I can't be on the same scale. Actually, not on the right-hand side. If it's positive, it's on the same side. And it's going to be bigger. How do I know it's bigger? There's another equation that I didn't put on here that I should have. Magnification is defined as the height of the image over the height of the object, which turns out through geometry to be equal to minus the distance image over distance object. Minus. What does that minus mean?
What?
Minus means that it's down instead of up, that it's inverted. Doesn't mean subtract. I know where you're trying to go, but no. So it means it's inverted. So there's roughly what it looks like. Now my distance is off because obviously my 30 is less than twice 10.
Wait, is it actually supposed to be down? Isn't it
Yeah, it's supposed to be down because we have the distance image is 30. So the magnification is equal to minus distance image over distance object equals minus 30 centimeters over 10 centimeters equals minus 3. So it's minus inverted, 3 times taller. All right, we shall continue on this on Friday, which is 1 week before spring break starts. And you notice that there was no homework due today, but there will be homework